Hello, my name is Henrik. I'm here to show you how to choose the best thruster for your needs. When selecting a thruster, there are several factors to consider. In this video, I'll give you an overview of the key choices you need to make and how to use the tools that Copenhagen Subsea has developed to help with this process. After you have filled out the configurator on our webpage, you will receive a quote on the most suitable thruster for you. We are here to help and provide for you to get the best product. When choosing a thruster, it comes down to three main decisions. The version, which refers to the size of the thruster. The configuration, which involves the propeller and mounting design. And finally, the number of turns, a standard defined by Copenhagen Subsea that determines the motor required voltage and current in order to deliver the required RPM and thrust at a given power. These choices directly affect the thruster's performance and efficiency. Additionally, consideration should be made for how the thruster will be mounted and whether there are any specific cable size requirements. But we will talk about those later. The first decision is regarding the version or size of the thruster. Larger versions tend to be more efficient. At Copenhagen Subsea, we offer 4 versions: small, medium, large, and extra large. This graph shows the thrust delivered by the thrusters at the same power input. You can see that the extra large thruster shown in yellow produces significantly more thrust compared to smaller versions at the same power level. The second choice is the thruster's configuration, which impacts its general application. The configuration determines the propeller blade design and inlet-outlet rings. There are 3 configurations to choose from. Symmetrical configurations are designed for vehicles that need to develop thrust in multiple directions, making them ideal for vehicles requiring high mobility. Asymmetrical configurations are optimized for operations in one direction, suitable for vehicles that primarily move forward. The compact configuration features symmetrical propeller blades, but without inlet-outlet rings. The compact configuration is ideal for installing in a funnel. The performance depends largely on how the installation and mounting is made. The last choice to make is the number of turns in the thruster, which influences the current and voltage relationship. This is important when integrating the thruster with the power source. Generally, more turns results in a lower required current but a higher voltage. Before we jump into the thruster performance lookup table, there are just a few more things you need to be aware of that may need some explanation. VRMS and V-peak both represents voltage required at the motor terminals, face to face, at each speed. VRMS is given since the motor is designed for sinusoidal AC voltage input, and V-peak is given as it represents the minimum required DC voltage in order to generate the needed AC voltage at the motor terminals. As the motor speeds up, it will require more power input, for example, a higher voltage, amplitude and frequency, as well as current, will be needed at its terminals. The required AC voltage is then achieved by a motor controller in charge of adjusting amplitude and frequency in order to control the power and speed of the motor. In order to do so, a controller can receive AC voltage from an AC power supply which it then rectifies into DC voltage and convert back into the AC voltage with desired amplitude and frequency, as shown here. Alternatively, a controller can receive a DC voltage directly and then convert it into the required AC voltage. This will depend on the type of motor controller. Regardless of using AC or DC power supply, you have to make sure that the power supply and controller are able to deliver the required motor voltage and current. You have to take these 3 points into consideration. DC bus voltage required. As an example, if your motor controller can receive AC voltage and it's supplied with 3 times 400 volt AC, then the available DC voltage will be 400 multiplied with the square root of 2, which equals 560 volt DC. Alternatively, you could also use a motor controller that can be supplied directly with DC voltage, in our example, a 560 volt DC power source. 2. Power required. Here you have to ensure your power supply can deliver the power required by the motor and that the controller is able to handle that power. In other words, you have to ensure both power supply and controller can deliver that power to the motor continuously. 3. Current required. And here also, ensure the motor controller is able to deliver the required motor current for the desired maximum speed. In general, we advise choosing a power source with 5% higher voltage than the needed voltage to account for conversion losses. Now that you understand the 3 main decisions, let me show you how to use our thruster selection tool. We have developed a lookup table for thruster performance that looks like this. The versions are listed under the orange bars in the table, representing the different versions: small, medium, large, and extra large. You can see that for each version there is a corresponding RPM, power input, and thrust values. The thruster configuration, asymmetrical and symmetrical, are listed for both forward and reverse directions. For symmetrical configurations, the forward and reverse settings are identical. The number of turns along with the required current and voltage is listed to the right. Let's go through an example. We need a thruster that provides 425 Newton of thrust with a power source of 120 volt DC. Also, we are choosing the asymmetrical configuration because this fits best to our application. Using the table, we'll look under the asymmetrical forward configuration to determine which thruster version meets the requirements. The medium thruster delivers the required thrust at 2000 RPM with 4.5 kilowatts. The large version can achieve the same thrust at 1200 RPM with 3.1 kilowatt, and the extra large version requires only 600 RPM with 1.6 kilowatt. As you can see, the larger thrusters deliver the same thrust with significantly lower power input. Now, when we combine all these information, we get a clearer overview. As mentioned earlier, the version small thruster isn't suitable for this application as it cannot exceed 200 Newton of thrust, which is well below our target. Next, we need to determine the correct number of turns. To do this, we look to the right side of the lookup table. If our power source is 120 volts, which number of turns should we choose? The right number of turns is the one where the voltage is closest to but not higher than what the power source can supply. If the voltage required is higher than what the power source can deliver, the thrust at a given RPM won't be achieved and the thruster performance will fall short. In our example, we have a DC power supply, therefore we look in the V-peak columns. For the medium thruster, 8 turns requires 115 volt, making it the best fit. 16 turns exceed this at 230 volt. Similarly, for the large thruster, 7 turns is the correct choice because 13 turns requires too much voltage. For the extra large thruster, 11 is the best choice with a voltage of 107 volt, while 19 turns is too high. In this example, the extra large thruster with 11 turns delivers the requested 425 newtons of thrust most efficiently. Now, just 3 more things you need to consider which are related to the mounting of the thruster. The current demand determines the required cable thickness. The larger the current, the thicker the cable must be. Here we show an example of how current and cable size are related. For the large thruster with 2 turns, shows the cable size increases significantly as thrust increases. You can see the cable specification in different color gradings in the lookup table. The physical dimensions of the thruster is something you need to keep in mind in many cases when you design your vehicle. The physical dimensions of the thruster are listed at the Copenhagen Subsea website. You can also request a 3D file. Finally, you should consider the installation of the thruster. The thruster can be mounted as symmetrical version or asymmetrical as demonstrated earlier, but also as the compact version as you see here, which does not include the inlet or outlet ring. The compact version can be paired with a custom designed funnel or integrated into your application in various ways. And lastly, there is the option to mount it using the Copenhagen Subsea AUV mount. Now that we've gone through everything, I hope you have a better understanding of how to choose a Copenhagen Subsea thruster, review the different versions, configurations and number of turns to find the right fit. Thank you, and I hope this video will help you choose the perfect thruster for your needs. Have a great day.